If you were to place a hydrophone into this picture, what would you hear? You would hear the sound of wind blowing over the ocean. Yes, this is one of the dominant sounds recorded underwater. You would hear waves breaking on the shore. Perhaps you would hear the sound of ice cracking in the Arctic, or perhaps you would hear a subsea volcano. Together, we lump these sounds as geophony. You would also hear marine animals like whales, dolphins, fishes, even crustaceans. These make up the biophony. And you would hear us, humans, out on ships, rigs, or diving, the anthropophony. The ocean is a dark place, and so animals evolved to use sound in support of their major life functions. Animals use sound passively by listening and actively for communication, for example, during reproduction. For example, male fish sing on spawning grounds. Or for the rearing of young, and an example are the mother-pup contact calls in seals. Or for the coordination of group behavior. They use sound for environmental sensing, predator detection. And don't forget that toothed whales and dolphins have an active biosonar system. They emit clicks and they listen to the echoes. That's how they navigate and find food. Let me give you a few more examples. Male humpback whales sing as a form of sexual display. All males in the population sing the same song, yet song changes over the years. In the top figure, you see the evolution of song in the East Australian humpback whale population over the course of 3 years. During the southern migration in 1995, they all sang the same song. In 1996, a few animals sang new, different song. During the northern migration in 1997, many more animals sang the new song, with some singing an intermediate mishmash. In 1998, they all sang the new song. What was interesting here is that the new song type was the song previously sung by the Western Australian population, the West Coast Swing. So where do these animals mix and hear each other's song? Or do some individuals change coasts? The bottom figure implies that this could only happen in Antarctica, where these animals migrate to every year and spend their summers. Killer whales have acoustic dialects whereby different family groups can be told apart. In the right picture, you see the same call type, N9, made by 3 different pods of British Columbia, Canada. Pods A1, A4, and A5. On the x-axis, you would have time. On the y-axis, you would have frequency. And the dark lines in these spectrograms show where the acoustic energy sits. You can see differences between the pods. For example, pod A1 misses the 4th component of this core. The dendrogram on the left shows the similarity of calls across pods and clans, and interestingly resembles genetic relatedness. Dolphins emit signature whistles, by which individuals can be told apart. They use these when separated from the group, but also when groups come together. There's a spectrogram of a looped, upsweeping whistle in the right plot. In our study, we looked at associations of individuals based on visual and acoustic recordings, and the probability of citing a specific individual when a specific whistle was recorded. Knowing which individual dolphin makes which signature whistle would be immensely useful for passive acoustic monitoring of this population. Not only marine mammals use sound, though they have been studied more than other species. For example, in one groundbreaking study, it was shown that the larvae of coral reef fish listen to the soundscape to find habitat suitable for their settlement. The question then becomes, do these animals find their home reef in the presence of noise? When humans take to the ocean, they generate underwater noise. In the top figure, you see sound sources of a pristine ocean, full of natural sounds from animals and the environment. In the bottom figure, you see the ocean of the Anthropocene, with ships, seismic surveys, construction, pile driving, etc. Underwater noise is a far-reaching problem, because sound propagates so well in the ocean. The top plot shows how sound from a seismic survey of Australia dissipated through the ocean and was recorded in Antarctica. Here the seismic survey noise was 100 decibels quieter, but still detectable above ambient levels. The bottom plot sketches how sound of Antarctic ice cracking is monitored with hydrophones off Australia and Diego Garcia in the Indian Ocean. That is 6,000 to 7,000 kilometers away. And so imagine how sound from multiple sources may fill the ocean. What does noise do to animals? Particularly for marine mammals, but also fishes, research has shown that sound may cause stress, even at low levels or long ranges from the source. It can interfere with the acoustic sensing and communication, an effect we call masking. So I've got two examples here. In the first example, you will hear a beluga whale call and ship noise, and you can identify the call quite well through the noise. In the second example now, the ship is much closer to the whale, so it is much harder to hear the whale sound in the ship noise. This is what we call acoustic masking. The noise interferes with the sounds important to these animals. Noise might also lead to behavioral changes, for example, in orientation, breathing, vocalizations, diving behavior, resting, and animals might show avoidance. It might lead to hearing loss, which may be temporary or permanent at loud levels. Noise might also cause physical damage to tissues and organs at very extreme levels. While the effects of noise on individuals have been well documented in marine mammals and fishes, questions remain on how these effects translate into population-level effects. For example, we can easily quantify, measure, and model noise. See the green box. And there have been many studies on individual effects. That's the orange box. But if the noise temporarily disrupts feeding or breeding, now in the gray box, does this lead to an overall reduction in reproductive success, which is the yellow box? And does this ultimately lead to population decline, which is the blue box? There are still a lot of unknowns. What we do know is that the problem is getting bigger and we are racing against time. Several studies have documented a steady increase in ocean noise, in particular at low frequencies, over the last 70 years. And the increase is roughly 3 decibels every 10 years. Part of this increase is due to the steady growth in maritime transport, with more and larger ships. So what can we do about noise? Most countries have regulations protecting species and their habitat, even though noise might not be specifically mentioned. Some countries have regulations or guidelines for specific types of noise, such as marine seismic surveys or pile driving. There are common approaches to mitigating the effects of noise. For example, observers might be placed on vessels or on shore looking for animals. And if animals appear within the so-called safety zone, then the operation might have to temporarily stop or reduce power until animals have departed. Acoustic monitoring with hydrophones is often used in addition to visual monitoring. There are things you can do to the source. It might be possible to use a quieter source or use alternative technology. Operational parameters such as ramping up the source have been used, even though it remains unknown whether sensitive species would indeed move away if the noise became too loud. Noise buffers can be installed in certain cases, for example bubble curtains around pile driving in shallow water. Maybe the operation can be timed outside of the critical season, like the whale breeding season. There remain a lot of challenges, which I've tried to group depending on whether they are challenges to science, policy, or society. There are still lots of unknowns about the impacts of underwater noise in the majority of species. Little is known about cumulative impacts from multiple exposures. For example, if whales on migration experience multiple seismic surveys, one after the other. Little is known about the interaction of noise with non-acoustic stressors. If animals already suffer from prey depletion, do they cope less with noise? Some studies are commissioned or classified, and so the results are not publicly available. Humongous amounts of data are collected during monitoring, but do not flow into the public domain, and hence do not advance science, and this is a loss to science and the environment. There is a lack of standards, even for noise measurement, analysis, and reporting, which is a problem that starts within the scientific community. Science transfer into policy is slow. New regulations need to be reviewed, opened for public comment, and pass through several layers of government. Underwater noise is a transboundary pollutant because it travels so far. So while the noise source might be located in one country, the noise travels across borders into other countries. And different approaches are used in different jurisdictions. There are lots of international agreements, but they all lack tangible guidelines. Regulations also need to be multivariate and flexible because one number won't suit all of the cases. There can be conflicting interests of the different stakeholders in the marine environment. And finally, what needs to be improved is stakeholder communication and liaison. Thank you.